Biba, this is for Biba. This is assignment 18. This on the e-calculation. And look like you're having a problem with us on the assignment on number 6. Let me see, share. Let me see, share this one. Okay. All right, so we're looking at your okay, so if you look at the formula wise, you look at, okay, look like you're having this one right here that you were having problem with. Okay,
Yes.
so so the formula is at VCC minus IC times RC. Okay, so we know that VCC is 10 VDC already. So VDC is the base, it's in volt. And your IC was calculated here. It tell me that it's in milliamp, okay? So this one is unit is milliamp. So we have to convert this one into the base unit first, okay? So this step must, so you have to solve this one first. So the first thing you want to do is just saying that, so the line before you doing this formula is to do IC is equal to IC divided by 1000, okay? So the purpose of this is to converting milliamp to amp. Amp is the base unit, okay? And now we can do, and then on the next one, we can apply that formula. So double VCC, VC equal to VCC minus IC times RC, okay? Because we know that VCC would be in base unit, which is, like I said, it's in volt. And then RC is in ohm, which is base unit. So the only one that wasn't in base unit was this one right here. It's in milliamp. That's why we have to convert it first before we can use it here in this formula. Okay. You follow?
Yes, I'm
Okay.
following.
Okay. So yeah, once this is done, and then you do this one, and you should be okay. And you should be able to run your program, and it should be able to pass it. Okay.
Okay, I'll try it again.
Okay. All right. So anybody have any other question? Okay, so for our Tech 2 student, I'm still, we're still having quite a bit of problem with Tech 2 student. You guys you're still not following the direction, okay? You guys still having problem not following the direction and completing the assignment, okay? So for Tech 2 student, okay. As you can see, so this lady still failing test 1, so DLAB number 1 fell there, and fell here. And Mr. 1 here, I cannot open up your file from the website. So let me see if 1 is in here. So 1 is not, 1 is, okay, Juan de los Santos. Okay, Juan de los Santos. Okay, we're unable to open up your file. Let me go ahead and go into the website and show you, okay? All right, so this is a website. Let me see, go to here, and this is assignment for Tech 2. So I'm going to scroll down to Tech 2. Okay, one, look like down here, L, okay, JKL, okay, so J, okay, K, nope, you're not De Los Santos, so we, De Los Santos. Okay, Juan, you will be over here. Let me go ahead and enlarge this a bit. Okay. What you want to do is make sure you just put name of your lab right here, logic gate dot XLS. Don't put this a lot more, these extension. As long as you put plus plus, it means something else when you put it into the computer here. When I click on one of these, as you can see, it gives me a whole bunch of errors. So I cannot open up that file. Okay, make sure you re-upload that file, so I can be able to run it. Okay, so that's the first one. This one I cannot open. As you can see, it gave me a whole bunch of errors, so I cannot open up. I cannot do anything with it. All right, so, and then this one right here, the, okay, so the next one, number 3 here. See, in number 3, you did it right. So this one doesn't have that little bit of plus in between here. I can open that up. I can open up, as you can see. I can click open it, and then it open up right away. Okay, so therefore, and let me see, as you can see, there it is, it's able to open. So the other two, make sure you redo that, and just like I said, just put the name of the assignment, and that's it, with the dot extension XLSX, and that would able to cover that. Okay, just like similar to this one. So don't put this additional part right here, and C++ and C++. When you put that, I cannot open up the file. So there's nothing I can do with it. On the assignment 3, I think you, on the assignment 3, look like, yeah, assignment 3, you pass assignment 3. So just make sure you go back and do just number 1 and 2 again and re-upload that. I think that should be, once you do that, you should be good to go. And then, like I said, it look like we still have student that's still having problem with DLab 1. It's still failing here. Test 1, test 1, test 1. Okay, failing test 1. All 4 students still having problem on failing test 1. Okay, DLab 1, and then DLab 2. It's the same group of people still failing the same thing. And then DLab 4, it's the same thing with that. Fail test 1, test 1, test 1, test 1. So I don't know what you guys doing, but it seems like you're not doing the right way. Okay. Make sure, yeah, we did have the recording that was on the website. You had to go watch that, how to do that program. Okay, we did it. I think we did it 2 or 3 times already, and it's recorded. It's on the website. So make sure you go through that website and do according to what we recommend you do. Okay, so because it look like everybody else are able to successfully complete it, the first one. As you can see, this gentleman is brand new and he's able to do it. And Catherine, she's able to do it. Mr. Mehdi, able to do it. Kumi did it. And then we got Mr. Michael is able to complete. And we got Ben Chi here. He's completed his. And Viola did her. And Adam, he did it, completed his. Mr. Smith, he completed his. And Jimmy True, he completed his. Okay, so we still have quite a bit of problem with the student. Okay, so like I said, make sure you get at least number 1, at least get 1 right. It seems like you guys keep on turning assignment, all fail. Test 1, test 1, test 1, test 1, and test 1, test 1, test 1, test 1. That's not good. Okay, because it's failing the same problem, because I see that you're copying exactly from this test, you put it into the second test. So if this one's going to fail, it's going to keep on failing throughout the other tests. Okay, so make sure you do it the right way, the first one, and follow that process. Okay, if you keep on doing this way, it's going to keep on failing. Okay. All right, so any question or?
Yes, I have questions, Sam.
Okay.
I already upload the last test version from
okay, so
27 October. Yeah.
Okay, so you upload it right here, right?
Yeah. You
okay. Which one? Down. Which one?
Yeah. That's the one. The October 27.
This one right here.
The last test. Yeah.
This one right here. I can see it right away. It failed right here.
It failed.
Right here, it failed. Why? Because I can go back into the website. I go to the website. I go back into the handout. The sample program, the electronic for digital technician. Okay, so here's a sample program right here, and I can look at the sample program. Test 1 right here under test number 1, test title. Here's it, expected data. Why do you have why do you have expected value? Where are you getting that from? Okay.
Oh, I followed the Excel I might do it in Excel.
Look, this is a sample program. Mr. Pham already give you a sample program. You have to follow the sample program. Yeah, you change to according to whatever you're on your Excel, but the sample program, this is a sample program, right? Because then you have this expected data, and then when you do the measured data, it's measuring data here. And so now they're testing the evaluation. They're going to take the expected data and compare it to the measured data. Did it have right or wrong? But here you have nothing. Here they're going to take expected data. Where's your expected data in test one here? There's no expected data anywhere here. Okay, so they can't compare this and this together. Like here, they can, because here they can compare it to this one because this expected data is from this line right here.
Yes, I will.
Okay, use this as a sample program. We keep on telling you guys and you guys not doing it. And I will look at it and I just run the test. It will fail test one no matter what, because there's nothing here. There's no expected data that can compare to the measured data, okay? All right.
Where it says expected value, he wants you to change that to expected data.
Use this sample program. Use this sample program and then change it to whatever it is according to your Excel, or whatever your expected data on your Excel, put it here. Whatever your mass data on your Excel, put it here. And whatever the test title for your test is, put it here. And then whatever you pick off, put it here. And then whatever you input, either port A, port B, port C. If it's port A, changes to A, and then change whatever the hexa value here, okay? So that's the only way, because everything else look like, if I'm opening up like that, I look at the same thing. You said it's fixed here, but if I click on here, it's the same thing. Here is an expected value. And then when expected value, and you got this one here, when they're getting the answer, and then they're going to assign it to measure data. So now they have this measured data, they're going to compare it to expected data. Well, if there's no expected data anywhere in test one, how can they compare anything to it? Okay.
Sam, question?
Yes.
While I'm watching you explain, thank you for doing that. I'm just trying to understand where he would have got the expected value. Where's that coming from?
This one is when you get into when you look into the lab where you're going to have the analog. No, you're converting digital to analog because you need a value. A value is same thing like if you need to see the voltage of from your meter, right? If it's at 3.5 volt, okay.
Right. Yeah.
That's a value. Okay. This is this is a data that we're expecting.
No, I understand what you just said. I'm just wondering where he might have referenced something and he might have got confused. And
sound like they got something from the e-calculation where it says value, but they shouldn't have used that. Not but for
then even then, it's not anything on the. Let's see. Okay, so if I go into the handout here, okay, so handout from Tech 1, so we got look sample program, so Tech 1 sample test, and then we're going down here, it's a sample program, e-calculation sample. Okay, if I open up that, okay, so we're gonna look at that. Okay, so let me see. So this one is that doesn't have the program, but let me open up the other one. Okay, so we're gonna okay, XLS. So this one is a sample. So this one right here. Okay, so that one is Excel also. This one Excel. Oh, this one text right there. Okay. All right. So even in test one. Okay, so this one, yeah. Okay, you're right, Mrs. Smith. Okay, expected value. Even this. So yeah, like I said, to use exactly from the program from. Yeah, you're getting from the wrong place. So like I said,
that's what I was going to say, Sam. They're copying the wrong example.
Handout. You guy is in digital. So digital is from this one right here. So use a sample from the digital sample program. And for Tech 1 is from the electronic lecture, that's a sample program. It's this here. Okay. So that's that. So for the Tech 1 assignment is this sample program. For Tech 2, you got on digital. So digital is right here. So this is from the sample program. D Lab 1, see? D Lab 01 Fall 2020. You guys doing D Lab. Nothing had to do anything about e-calculation. So you copying the wrong sample program. Okay. So that's pretty much it. And we're back to Mr. Pham.
Oh, and Mr. Pham.
Yeah.
Well, Sam checked it, but I finally got my parts, so I built it too. So I did D-Lab 6, it runs and everything with the 4 thing. Only one thing is, I got 2 of those control boards. One of mine don't work, but since we're not at the lab, I'm not able to get it to you to get it fixed right. But I got one that's, I guess you could say it's working now because I passed the D-Lab 6 on one of them, but on the other one I didn't because there's something wrong with it.
Okay.
You mean D-Lab 6?
Yeah, D-Lab 6, I got it to pass and everything. I built the circuit at home.
Okay.
Okay, look like another one that
have to download the up-to-date D-Lab 6.
Oh, you mean on the Excel?
Yeah.
Oh, you read it? Yeah, because that for a long while your Excel wasn't working right.
I already fixed it.
Okay, the whole thing?
Yeah.
Okay, Mr. Pham.
Okay, it looked like another one was question assignment 24. Okay, this is Jihan. Okay, what on assignment 24, do you know what question you want me to go over? Because there's there's quite a bit on there. So you want is particular, is there which number do you have problem? Number 4. Okay, number 4. All right, so number 4. All right, we're gonna do number 4. Okay, so I'm gonna write in here. So this is in, and then you got your first amplifier, and then you got your filter, and then you got your amplifier, and then you got your filter, and then you got amplifier, and then you go out. Okay, so this is your attenuator, or attenuator is the same thing as drop in signal. So this is 3 dB. This is attenuator. This is 3 dB. Okay, so they said that they're gonna put in 3 dBm to come in as in, so 3 dBm. And this one's an amplifier, so this is positive 10 dB. So this is 10 dB. This is 10 dB. Okay, so this is your amplifier number 1, number 2, number 3. And this is your filter filter or your attenuation number 1, attenuation number 2. Okay, so therefore it's the let me see. Yeah, probably not very clear, but
yeah, very clear.
Okay. So now you want to do is, so your out would be equal to your in plus your amp number 1, A1, minus your attenuation 1 plus your amplifier number 2 minus your attenuation number 2 plus your amplification of number 3, and that should be it. Okay, so therefore you take a 3 plus a 10, so 13 minus a 3, and so that's come back to a 10, and then plus a 10, so that's 20. 20 minus a 3, so that's 17. And 17 plus 10 equal to positive 27 dBm.
Can you make that bigger so we can see it?
It's really big.
Okay. So it's something similar to, let me see if I can do it, this one. Let me maximize this one here. Okay, let me share, okay, so you'll be, stop sharing. Oh, did you get that from the?
Now put it up, now put that up, Sam.
Okay, let me see, share screen. Okay, so like it's going to be the in plus your amplify number 1 minus your attenuation 1 plus your amplify number 2 minus your attenuation number 2 plus your amplification number 3. So therefore is equal to plus 3 dBm plus 10 dB minus 3 dB plus 10 dB minus 3 dB plus 10 dB. And so your answer at the end should comes up to, you add them all that up, it should comes up to 27. And it would take in the form of dBm, dBm, okay? So that's pretty much it, just adding across just from the input all the way to the output. Okay, so do you have any other question? Let me see. Okay, number 4. Look like you're good to go. Okay, very good. All right, so go ahead, stop this. Okay. All right, so back to you, Mr. Pham.
Okay, thank you, Sam.
Thank you. You're welcome.
Okay, so we get 6 more weeks to go. And not every week you can get the 1/10 on the Tuesday tomorrow. Okay, the test will be run this way. First time, you follow it and do it. Then after the test completed, you upload your report. Okay. Then after that, I will be upload the whole test on the website. So now you do again a second time, giving you more time, few days to complete it. And that is the document need for you guys to job interview. Okay. The question very simple. We expect you can do it right away without looking into any notebook or the data book or the whatever. Okay. So today we will go with the ZenerDiode. That's the first thing. The second thing we go to the comparator, differentiator, and also integrator. Whatever we left over, try to get through it. Okay? Make sure you download the diode handout for the handout for today. Okay, now you can see that's a ZenerDiode. So basically, this is a symbol, okay, for the ZenerDiode, anode and this is the cathode. And they will be look like this guy here, okay? And basically this side will be positive, this side will be negative. So they say a major application for ZenerDiode is the type of voltage regulator for providing stable reference voltage for use in power supply or even in the voltmeter or and another instrument. Now, the ZenerDiode will be working two ways. If they break down, they're working like this guy here. It's a breakdown, okay? However, they can be working like normal diode. So this will be a positive and this will be negative like just normal diode, okay? So when you see the symbol, you're able to recognize this is a ZenerDiode and must know how they be working. Is it a breakdown or they working just normally diode, okay? If you get any question, anything, just bring it up. We try to make it clear for you guys.
Mr. Pham, when does this breakdown diode act like a battery with the positive and the negative at the bottom? What is the voltage on it?
What is the voltage on that for a Zener?
Yeah, is this still 0.7?
We don't know.
Oh, we don't know. Okay.
If you go to buy the Zener, they will be ask you what the Zener voltage you want. Then you can say 5 volt, 10 volt, any voltage.
Okay. All right. Thank you.
Yeah. And here I just bring it up to you, make sure you understand. Zener can be working like they working breakdown in the breakdown diode, or they working just like normal diode. That's it. Now, on this circuitry here, okay, they say for the circuitry, they given VZ. That means the breakdown, 10 volt. If you get a 20 volt, DC apply here. The question is what the voltage here.
Ten volts.
Exactly, 10 volt. Now, I try to explain to you how the Zener here, they will be breakdown. No matter what, any voltage on this side higher than 10 volt. So that's why in the power supply, you get the output 10 volt. So they want to put a Zener in there. Guarantee no matter what input, you can get more than 10, then the output still be 10. That's why they break down, okay? So the answer here, okay, we can say V out 10 volt. The thing is, Zener will be breakdown.
And Mr. Pham, so it's really not 20 minus 10?
No, that is different story. Right now, we're talking about VR.
And the VR by mean is a 10 volt. That's right. V drop at the R is 10 volt.
We drop across R.
Yeah, 10 volt.
Difference between 20 and 10. You get one side of the R will be 20. Another side at the VR will be 10. The difference will be 20 minus 10.
I mean, it's a the voltage drop at the R is a 10 volt.
20 minus 10.
Mr. Pham.
Yeah.
So without the part number, the 4740, how do you know if it's Zener or not without that part number? If it's not there, how can I know the difference?
No, the thing is, normally they can be any part. When
Okay,
you buy
so
it,
it always come with a part.
yeah, you can get any part.
Okay.
Okay, the thing is when you buy it, they asking you what the
The
breakdown.
part number. Okay.
And Mr. Pham, if I could just ask one last thing. So based on where the Zener is located in this circuit, and in the example, it says VZ is equal to 10 volts, and
Right.
VZ is a breakdown voltage that is 10 volts.
Right.
So then, therefore, the output is 10 volts.
Output cannot be higher than 10.
Okay, thank you. Can it be lower?
Yeah, they can be lower, but they
But not higher.
higher.
Another question, Mr. Pham.
Yeah, go ahead.
So the output depends on the ZenerDiode that you would attach to the circuit, right?
Yeah.
And the Zener voltage caps the output voltage at that level?
Yeah, they must be. If any voltage at the input higher than 10, like we in 50 volt, no matter what, output will be 10. The Zener will be breakdown. And if you want to calculate the voltage, the current go through the resistor, you have to take the difference between V in and the 10 volt of the Zener by the resistor. So, number 2, what is the current through the 120 ohm? So basically,
45 milliamp?
Yeah, I don't calculate, I don't know. But I can give it to you. IR equal.
I agree with that, Catherine.
20 minus 10 divide 220. Okay? Now we go into they say I get minus 5 ohm. And they're asking to get what is the V out.
0 volt.
0.7? Oh, wait.
Telling me.
0 volt?
Yeah, 0.
Okay, not yet. Before you decide what the V out, you have to know how the Zener working. So now you get a minus 5 here. Right?
Oh, minus.
That's what I said. If I change it to the minus 5 volt, what is the V out?
So now it's acting like a regular diode because it's
Well,
forward.
now they're working like just a ZenerDiode. On the one side will be ground, means 0 volt. The other side minus 5. So that the diode will be on normally. Okay? When they on normally, what happens is you get positive here, you get negative here, and the value will be 0.7 volt. Okay? So on number C here, what we can say, Zener on normally. So that V out equal minus 0.7 volt. can see the circuitry very simple. Just asking for required understanding.
Mr. Pham, I have a question.
Yeah, go ahead.
What if the V in is negative 7 volts? Then also the output will be negative 0.7.
Exactly. Any voltage negative. Then
As long as the Zener is forward biased,
yeah,
it can be any voltage.
That's what I already showed you at the beginning here. Okay? You can see that. If you get a ground on this side and my negative 5 on the other side, diode just working normal. They will be on. And they on, they can be substituted by the battery. Positive here, negative here, minus 0.7. That's what you get here.
Yeah, I have one more question.
Yeah.
What if V in is 3 volts?
Okay, so you want to say you get 3 volts.
If V in is 3 volts, what will be V out?
Okay. Now you say you get plus 3 volts. Right?
Yes.
Okay. So you can see, and this point you get 3. Right?
Yes.
So the Zener is not breakdown. Okay? And they cannot be on normally. The thing is the other side will be 0 volt. So the output will be 3 volt.
Okay, got it. Thank you.
Mm-hmm. Okay.
Mr. Pham.
Yeah.
Would that hold true with any input voltage that is under 10 volts? V out would just be the same?
Exactly.
Okay, thank you.
The thing is Zener not breakdown.
Right.
Look like they open.
But it should be positive. Am I right?
Can you say again?
The V in should be positive. Should be a bit less than 10, but should be positive.
Yeah. If they negative, they turn on the diode.
Okay, got it.
You can
Thank
get 3 volt, you can get 7 volt. Okay, 9 volt, that's okay. Not over 10. Then they just diode like open.
So when your input voltage is under 10 volts here, your output voltage will match the input. Right. Any input voltage over 10 volts gets capped at 10 volts by the diode.
Right.
Okay.
That's how Zener working. Guarantee no more, any more voltage higher than 10 volt can go out.
But you can choose, sorry, I was just saying, you can choose any value. It can be, you can have it made to your own specification of how your voltage level?
Yeah.
Okay.
Mr. Pham, if VR equals the VZ, then does that apply also series or parallel doesn't matter?
What do you mean VR?
For the breakdown voltage of the Zener equals the resistor voltage drop, right?
They will be not mean they will be voltage drop. They depend on the VG.
Okay, thank you.
Okay, last one. If they get negative 5 volt, what is the current? How do we calculate it?
Negative 3.18 milliamp?
Yeah, that means right here, you get minus 0.7 volt. And this side, you get minus 5 volt. So the current will be go this way. So I will be Okay, minus 0.7 minus 2 minus 5 divide 220. So that will be 4.3 divide 220. Oh. Make sure try to understand. So tomorrow you do the test, at least you get a 50%. Okay, any more questions? Otherwise, we go. Okay. Now, can you do it for me quickly? You see anyone can answer.
Is 12 volts.
Go ahead, go to A, B, C, D. Then I will go with you. Okay, you done it?
I got A 12 volts. B out.
Yeah, correct.
And B current IR 25 milliampere.
And B, the current IR equal 24 minus 12 divide 470. And now how do we calculate the load current?
VZ divided by 490.
IL V out divide IL. That means 12 volt divide 490. Okay, you want to calculate the IG. Okay, that means you can take the IR minus the load current. If you get any question, let me know.
How we got IZ? The current through Zener.
You want to read the current to zero, you take the total current IR, that total current, minus the current go to the load, IL.
You're saying that IR is equal to IT.
That IT, IR the same. Okay, you set current go here, one go here, one go here. So already know the current IL. Then you can take the IR or I total minus the current IL. Then you get the IG. Okay, any question? Look like okay, right? Now I ask you this question here. So I change 24 volt to 10 volt. What we out?
Ten volt.
10 volt.
10 volt.
Do you think so? First thing is
12 volt.
What?
Bây giờ cái thằng Verizon á, giờ nó bán một cái,
volt.
nó tặng một cái, nhưng mà phải mở đường like của nó. Sao vậy? Cái phone nó bị hư hay sao vậy?
Chính là
You said 10 volt. Is it right?
12 volt.
Okay, now, first thing you have to understand when you're working with the Zener. In this case, 10 volt input, Zener breakdown or not?
No.
No.
If not breakdown, they will be open, right?
Yes.
Look like no Zener. I think that one side will be round and the other side be 10 or any voltage. But they cannot working like normal. So they open. So you want to calculate the VO. VO will be 10 times RL divide R plus RL, voltage divider. So that's why if I change that in the test guarantee, you get nothing. I think if you wrong the VO, you can wrong everything. Wrong calculate the current, okay?
Mr. Pham, I have a question.
Yeah.
In the previous circuit, you said that if the Zener breakdown is less than 12 volt, then the same output you will get. And in the previous circuit, there was no load, and that's why it was same 10 volts.
Yeah, if you don't have a load.
Yeah. So if it is having a load, then we have to apply this formula. Is that correct?
Exactly.
Got it.
The thing is that in this case, look like you have a no Zener. They open. So that's why I asking for the understanding. Okay? Okay, now we will explain a little more. In here, I already given to you the answer. Okay, for the zener, you get the V in now will be the sine wave. Okay, and you get the VG. So the sine wave for the positive sine wave, if they greater than VG here, so they will be cut it. Okay, maximum will be VG. Okay, however, for the negative peak voltage here, so there's a ground here, and a negative voltage here, the zener will be on normally, and the output will be minus 0.7. That's how they work for one cycle of the sine wave.
Can you explain one more time?
Okay, now when we apply the sine wave into the zener circuitry, okay, for a positive cycle, okay, that means you get a positive voltage here. If that voltage higher than VG, so they will be cut it at VG, okay? However, when you get a negative cycle, that means negative here, ground here, zener just on normally. And that's why you get plus minus 0.7.
Got it. Thank you.
Okay.
So Mr. Pham,
Yeah.
so that one that you just explained, the circuit that you just explained, and the circuit directly below it, they're the same thing except for positive and negative half cycles. Is that correct? And the diode is switched around.
Right.
Because when the anode, when the anode is at ground, then you get it. You get that clipping on the top. When it's switched around the other way, you get the clipping on the top, but it's smaller, and the other one is VZ as opposed to 0.7.
Right. If the diode is normally on, so they will be minus 0.7.
And then the one below it, it's off or open.
No, on the fourth cycle, you have to say the first cycle positive right here. Therefore positive.
Right.
If the voltage at the input higher than VG, they cut it.
Right.
And that's how it works as a voltage regulator.
Right. Otherwise, when you get negative cycle here, the diode is on normally, then you get minus 0.7.
Why is it always 0.7?
How would that work?
The diode is on normal.
Is it because of the chemistry of the diode?
No, just the diode is normal. You understand that if you get a negative 5 volt here, then the diode is on normal, ground here, negative on the other side. So when they on, they will be like the battery. And the battery will be positive here, negative here, and the value will be minus 0.7.
I understand a diode can have multiple voltage levels, but why do diodes always have, by percentage, always 0.7 volts? Why is it always 0.7?
No, the thing is we're using silicon diode. You get only 2 different types. Germanium will be 0.3.
Do they make Did they make the Zeners out of germanium as well?
Yeah, that's normal.
Okay.
What Mr. Pham is saying, there's two types of diodes, silicon and germanium. Germanium is 0.7 and silicon is 0.7 and germanium is 0.4.
0.3.
3, 4, whatever.
Now, the silicon diode, 0.7.
Correct.
Germanium, 0.3.
Correct.
However, you can see on of the data they're using for silicon. They're not working with the germanium.
Right.
Germanium's more expensive, right?
Yeah. Just a different type of the diode.
What has the clear signal?
Right. But they're not using for picking. That is right now at this time, they can using germanium. Okay. Now on the second thing here. Okay. They basically you can see they just opposite.
Right.
Okay. If you get a positive here, okay, you turn on the diode. And that diode will be 0.7. However, if you get a negative here, and this side will be routed, so the Zener will be break down, okay? And the output here have to be, maximum will be minus VG. And now you can see the last example here. They get two Zener. So every time you can get the Zener D1, D2. If D1 break down, then D2 will be on normal. And the other side, if D2 break down, then D1 will be on normally. Okay? So for positive, okay, then D1, let's see, VG1 plus 0.7, okay? So that means D1 will be break down, D2 will be on normally. And also the same happen when you get the negative cycle. Then VG, I believe the first one will be VG2 breakdown. The second one will be VG1 breakdown. So the book will be wrong.
Hey, Mr. Pham, can you use your marker pencil and mark with plus or minus the anode and cathode?
I believe that's supposed to be VG2. VG2. This is VG1. Now,
okay. But what I'm saying is on the schematic itself, on the diodes, can you mark like which side of the anode or cathode is plus or minus?
Well, you can say this is the anode here, right?
Right.
This side will be cathode.
So, oh man.
We're talking about positive here. If the positive here higher than VG1, then D1 will be break down. No, D2. D2 will be break down. So that's why this has to be VG2. However, for this guy here, okay, you get positive here, you get a round here, they just turn it on. So this will be positive here, negative here. So that's why they plus 0.7. Okay, now I explain to you on the second one. Right now we go to negative here. if the negative here, okay, so basically, let's see, this is the negative and this is the round, okay? So this D1 will be breakdown. However, D2, you get a negative here, then 0 round here, so D2 will be on, okay? And when they on, and also you get a point here, you get negative here, so that's why it will be minus to 0.7 volt. Every time when you see two diodes connect this way, for the sideway, one will be on normal, one will be breakdown, okay? For either positive or negative of the Zener.
Hey, Mr. Pham, one thing that the clipping, what is the effect of the clipping of the signal, the way they clip it like that?
Now
What
they want to limit it by the Zener for both sides.
I guess what I'm asking is the effect that they're trying to make a square wave. Is that the reason for doing that?
Yeah, depending on the signal output they want. But to us, what we need to do is make sure the output, how they will be look like.
If you put a capacitor in the circuit someplace, would that increase the faster the capacitor charge time is?
Yeah, if you go to put the capacitor, they just try to charge it and discharge it. And also they can keep the voltage level more stable. Okay, now you can draw for me this one. Both Zener. And now they given you input 10 volt minus 10 volt sideways. And one Zener breakdown 3.3 volt. And another breakdown will be 5.1 volt. So for the positive cycle, what output look like? That means for the positive here, what we our voltage supposed to be?
5.1 plus 0.7.
Fourth Zener or second Zener will be breakdown.
Second.
Perfect. That means you get 5.1 plus 0.7, right? You see they look like 5.1 plus 3, 5.1, 0.7. That's why you get 5.8. Okay? On the first positive cycle, second Zener will be breakdown, and the fourth Zener will be working normally on. On the second one, what we are? On the negative cycle of the input signal, that means you get minus 10. What we are?
$2.6.
That means the first Zener will be breakdown, and the second Zener will be on normally. That means you can get 3.3 plus 0.7. That means you get -4. That's how the output will be look like. Okay. This is also they given you another example, but you're working on that to guarantee you can get 6.9 volt for positive cycle, and you get -15 volt 0.7 for negative cycle. Again, for positive cycle, 15 volt Zener will be on normally. 6.2 will be breakdown. So 6.2 you adding to 0.7, you get 6.9. And the second half, -20 volt. So the second one will be breakdown, 15 volt, -15 volt. And also the first one will be on normally and -7. So that's why you get -15.7 volt. Okay, what else? Comparator. Okay, comparator, basically they compare between the positive input and the negative input of the op-amp to see which one will be higher. Okay, if the input positive higher than the input negative, output will be go into the plus V saturation. Sometimes they say V out maximum. Okay, and if the negative input higher than the positive input, then output will be go to minus V saturation or minus V minimum. When you're looking into the circuitry, you're able to recognize, is it inverting amplified, non-inverting, follower, okay, or comparator? How do we know? This is comparator. If you're looking into the circuitry, how do we know or recognize this is a comparator circuit? It's not inverting, non-inverting, or a follower.
Whether the input signals to the positive or negative. In this case, positive.
Easy to recognize. I can tell you. They have a no feedback. You can see that. From the output, they don't have anything feedback into the input, positive or negative. So they be a comparator. On this circuitry, they call it zero level detection. What that mean? That means they compare with the route. Positive, you get a sideways. However, negative, you get 0 volt. They connect to route. Okay, so that's why they call it zero level. So comparator is a type of op-amp circuit that compare to input voltage and produce an output in either of two steps indicating the greater than or less than relationship of the input. Okay, and if you're looking into the timing right here, you get this is the positive. And the positive compare in with the route. So they must be higher than the route. So the output will be go into the V out max, or we can say V out saturation. That's okay. The thing is when you're looking into this timing diagram, you must be understand why you get this go to V out max. The reason is when they compare the input positive to input negative, and the positive higher than the negative. So that's why the output is Vout maximum. And when you get a negative here, right here, a negative this side compare to round here. So this negative now will be higher than positive. Output will be going down to negative voltage saturation, or Vout max minus Vout max right here. Okay, so that's why they go low here. Okay, and the question about basic comparator here. Okay, so no question. Now, they given to you 3 different comparator. First thing, you can say, I know this is a comparator. However, this thing will be a compare this sideway with the voltage, DC voltage here. They call a V reference. So try to say sideways compared to V reference here, which input will be higher. Okay. Then instead they're using the voltage reference power supply here. They don't want. They're using 2 resistors to get the V reference here. And this is just a voltage divider. V reference, in this case, they will be equal V plus here, times R2, divide R1 plus R2. Okay, so that's why they compare the input here to whatever voltage reference here. And the last one, they're using the Zener, make a reference. Okay, now, if I said VG (10 volt), and that one equal 30 volt. So now what they compare? They compare with what voltage?
10 volt. $10 volts.
10 volt.
All right. Why? The thing is, VG equal 10 volt. That means the voltage here, no matter what, they have to be 10. Okay? They must be 10 volt. They cannot be 30 volt.
That's because you treat the VZ equal 10 like this breakdown, right?
Right. So that's why input, they can come to any voltage, but they cannot be higher than 10 volt. So in this case, comparator will be compared with the 10 volt. Now, if I change that one, okay, five volt. So what the comparator compared to?
The 5 volts.
Perfect. Yeah, now you understand. 5 volt, that means not greater than 10.
So it's an open switch?
Is in open. Okay? They not break down. So that's why, in this case, they will compare to 5 volt. What I said, do not quite follow it, let me know. Okay? Otherwise, I believe, you're able to follow it. This is a very, very basic thing you must know right away.
And Mr. Pham, in that one so the since you got 5 volts there, the cathode is more, the cathode, I'm trying to, which one is more positive? The cathode or the...
You get a 5 volt here, that means you get a 5 volt here.
Right.
Then open.
Okay.
They not break down. You know why? The thing is they not higher than 10.
And since that's open, there's no voltage drop across the resistor.
Nothing. That is the key point. If they not break down, they not normally on. They must be open. Look like no zener there. They just draw that for you, okay, from the other circuitry. Now, example. The input signal as so is applied to the comparator circuit. Draw the output showing its proper relationship to the input signal. Assume the maximum output level of the op-amp will be plus minus 12 volt DC. Can you draw that for me? Before you can do anything, in this comparator, to compare to the reference, that means they compare to the voltage here. Okay? So what the Vref equals?
Voltage divider.
Perfect. Okay? Then you have to calculate the V reference. Equal 15.
15 times 1,000.
Divide 8.2, right?
Plus 1.
So what you get?
$1.63 volts.
Okay, you get 1.63. Okay, so this is 0 here, 5 on here. I can get any point here. That will be 1.63 volt. So the first thing, when input is 0 up to 1.63. So which input will be higher? Right at this point, 1.63.
The inverting input.
Okay, so V in for this part right here. V in higher or less than 1.63?
Less.
Less than. Okay, they're telling you input negative, input positive, which one higher?
Negative.
Perfect. Negative higher. So the output will be go to the maximum negative saturation. That means they can be go into minus minus 12. Okay. Then from here to here. Okay, that means input here higher than or less than 1.63.
Higher.
Higher.
Higher. So they're telling you the positive higher than negative. Output go to plus 12. So basically, they can be go into plus 12. So that is the negative here, minus 12 here. Okay, and they will go this way. Okay. And basically, they will be negative here, and they can get this one here, and they will be going as a side here. Okay, now I try to see I get the answer for you here or not. Okay, this is the answer right here. Okay, only thing you have to try to understand it. And then you can see when they less than, okay, 1.63, output will be negative right here, minus 12. And when the quantity here higher than 0.63, they'll go to 12, okay? Then on this side here, negative. So that's why they go to the negative here and try again, same thing. That is how the output will be look like. Okay, you need the time to look into that. Not easy to understand for the not much time. Okay. The other thing, effect of input noise.
Effect noise compare.
Okay, effect of input noise on comparator operation. So basically, they just give you this is a sine wave here. However, you get a lot of noise. Okay, so they try to find a way in order comparator can be working. See that? Reducing noise effect with the heterogeneity. So this is the circuitry, this is the input here with the noise, okay? And now they try to design the circuitry so they can be try to get the output, okay? Avoid from the noise. Let's see. This is how it's working. When you're looking into this circuitry, you can get a very misunderstand with the amplifier. I can guarantee when you look into this circuitry, you can think about what amplifier. You know what amplify?
Inverting?
If they're inverting, then the positive must be rounded, right? But in this case, they're not rounded.
So it is a follower, Mr. Fan?
No, follower don't have a gain. Don't have an R1, R2.
Common source?
No. This is a comparator. They look like the non-inverting.
Oh.
Now, why? For the non-inverting, okay, they have to be negative. And they have to be positive. Okay? And now they will revert it. So they will be a comparator. And they will be compared with the voltage right here. That's what they call LTP, upper trigger point. Okay? They calculate the upper trigger point will be V plus times R2 here, divide R1 plus R2, voltage divider. Okay? And if you're looking into that one here, they can get a point they call a VLTP. You can get that V by doing your calculation here. Okay? So basically they compare with the VLTP. Okay? Upper trigger point. Okay? And then they will be compared with the lower trigger point. You see. Now, when the input goes to the negative here, then this the voltage will be a negative here. So that's what they call a lower trigger point. Calculate the same thing. That means you take a minus voltage here, okay, times R2 plus R1. And now you can see you get a lower trigger point, this point right here, and the upper trigger point here. So the signal, when they apply input, they trigger right here, okay? That avoid, you know, like this one try to go up, or this a little up going down here. They cannot be triggered. So that avoid for the noise, too much noise, okay? For this circuitry, basically, we don't have to go into too many details on it. However, when you're looking into the circuitry here, okay, you have to know that a comparator, okay, with the hysteresis. And you have to know what is LTP, upper trigger point, and what is VLTP, lower trigger point. And how do we calculate that upper trigger point or lower trigger point? Upper trigger point, that means you take a V maximum times R2 divide R1 plus R2. Okay? And lower trigger point, then you can see This one, you can take the minus maximum V out times R2 divide R1 plus R2. Let's see. This is just an example I give to you, and you can look into that. How do they calculate the upper trigger point? How do they calculate the lower trigger point? Okay? That's the only thing what they want you to know. Okay, now output bounding. When you get the sine wave applied to the op-amp, and then basically you get a Zener connect from negative to the output. Okay? Try to understand. If it's the input positive, what happened? And this is you get a VG. If the positive input, what happened?
Breakdown? Zener will break down?
No, they not break down.
No, it
Operate like normal.
Yeah, it
Operate
operates like a normal diode.
They just working normal. And when they working normal, then basically you get a positive here, negative here, and the value 0.7. So that's why output will be minus 0.7.
So Mr. Pham, for the negative 0.7, is that apply if it's positive or negative, we still have to apply 0.7?
All the time I said diode on normal, 0.7. However, depend, okay? If you get a diode this way, if you say they on, I said on substitute by the battery. Positive here, negative here, and the value 0.7. If you on this side, then you have to get minus.
Oh, okay.
If you on the other side, you get 0.7.
All right.
Okay?
Okay.
Okay, now my question is, when you get the positive here, how come the Zener is not break down?
Can you repeat the question?
When you apply negative cycle, okay, then you say the Zener working normal. That's why you get minus 0.7, right? So why? How come? How come this on normal?
Because
Still, your question is not clear to me.
VREF is 0?
What do you mean we reference here?
Well, that the voltage in at the negative is 0.
No. The input right now will be positive.
Oh.
I can say 10 volt, for example. This minus 10. So right now we deal with a positive. Okay?
so then your anode is positive relative to your cathode, so the diode is forward biased.
Now the thing is this just a comparator. This is just a comparator. They compare negative in and positive input. So if you get a positive 10 volt, which one?
Because 10 volts is positive compared to the 0, which is the other reference voltage.
No. My question is, when you get a 10 volt input, positive, so the input negative and positive of amp, which one will be higher?
The negative.
Negative higher. Okay?
So it goes to the negative.
So the output will be go to the negative saturation.
Right.
And negative saturation, and the other side of the diode will be 0 volt. Right? Why 0?
Because the positive input is grounded?
Exactly. You already know VD. VD means the difference between positive and negative, right? VD equals 0 on the time. Okay? So that's why positive rounded. That negative, you will be get 0 volt. Okay?
Hey, Mr. Pham, is that like virtual ground in there?
Yeah, that can look like. Okay? But they're not virtual ground. Okay? The thing is, normally, if you get a round on the other positive and another one, you can call that a virtual round. Okay? However, they will be same 0 volt with the positive. And when they compare negative higher than the positive, output will be go to the negative saturation. So one side of the Zener will be 0 and the other side will be negative. So that's why Zener will be on normal. And that's why you can get minus 0.7. However, when you go to the negative here, okay, if you get a negative compared to the round, so positive now will be higher than negative. So the output will be going to the V out mic. And they will be limited by the VZ. So that's why you can see it right here. Okay? You can see right here, they can go to the VZ maximum. Okay? They can be not higher than VZ. So during negative cycle, the ZenerDiode will be break down. On the second one, they just reverted the Zener. Okay? So they working the same way. However, I want to emphasize in this example here, make sure amplify just the comparator. They compare between positive and negative. Okay? If negative input higher than positive, output go to negative saturation. If positive higher than negative, output go to positive saturation. That's the key point.
Mr. Pham?
Yeah.
Earlier you said we could tell it was being used as a comparator because there was no feedback.
Right.
So if we were looking at this one, how would we know?
The thing is you don't have any feedback except they add in the Zener. Then you must be understand that that's a comparator.
Ah, okay, thank you.
Okay. When you get amplify, they get a resistor feedback, right? Inverting, non-inverting. Or you get just a wire for a follower, okay? It's the same thing. Output bounding. Okay, they can be get 2 diode. Same thing. One diode break down. The other diode will be on normally. So that's why you can see output, they be swing between Zener off diode 2 plus 0.7. And the second one will be ZenerDiode 1 minus 0.7. Exactly the same. They call it bounding. That means no matter what your input, the output will be limited by ZenerDiode. Okay, so we can get this example here. Okay, we'll be explaining it tomorrow. Let's see what else. That example continuing. They given you the answer here. You get the time, try to look into that. Okay, and this op-amp integrator have nothing. Basically, we're talking. Okay, nothing go into the detail. And also op-amp differentiator. Okay, that's it. We'll be stopped here. Okay.
Mr. Pham, just one last thing. I don't want to take up too much of your time. Insofar as a Zener diode and just a regular basic diode,
right?
What determines whether or not if you use which one or the other?
Now, depending on what I'm saying is Zener diode can be used in the power supply.
Mm-hmm.
That means any voltage into the power supply, normally the output power supply will be get a Zener. I given you the example. For the digital circuitry. In digital circuitry, only power they're using will be 5 volt. You see that?
Right.
So that's why the power supply applied to the digital circuitry, that power supply have to get the 5 volt ZenerDiode. Then you can connect wrong into 10 volt or 20 volt. Output go to the digital circuitry will be limited to 5 volt only. Without this Zener, you apply 10 volt into digital circuitry, you cook on the IC. That is the main purpose.
So, okay. So the Zener is almost like a regulator then, right?
That's what they said. Just a voltage regulator.
Okay.
Okay?
All right. Thank you.
Okay. We'll see you guys tomorrow.
Okay. Bye-bye. Have a good night.
Thank you.
You are welcome.
Thank you.
Thank you, Mr. Pham.